remember, but it was somebody. Oh, Jackson. Wow,
you remember Jackson?
Yes. Well, it's a good question because there's 500 of them. No, Garth.
Wait, is there Jackson?
No, but there's 4 in that other
Four.
class. 4.
That's crazy. But
Yeah.
zero
Jack
here.
Bailey.
And at the very beginning, they all had masks on. I'm like, I give it.
Well, how many-
There's a Jack Bailey, a Jack, a Jackson,
Oh, Jack Bullock.
and a
So
Jack.
there's Bailey. There's
Jack Bailey, Jack Bullock.
Jackson.
And Jackson Garth. Yeah.
That's cool. That's
I mean, what in the world? I mean, having 2 Carolines is like one thing, but like 4?
There's a lot of Jacks in this like our grade. Jack and Caroline are the most popular names.
I got a Caroline. Like I named one of mine Caroline. So I get it. All right. So here's the second kind of strange sum we're going to deal with. So again, this is the way you're going to enter this quiz. You're going to look at it and you're going to go, and I'm not going to focus on arithmetic and geometric at all, but the reason why I'm saying focus, I don't even know that there's an arithmetic thing on there, but there are arithmetic elements that you look for. And then it's possible on this quiz that you might have 2 geometrics woven together, right? And you'll see a couple of those on the review as we're going through there. But normally you'll go into a quiz and you'll go, all right, sequence and series time, or you go to a tournament and you look up there and you see a sequence. And by the way, when you would go to a tournament, you would look at this sequence and you would not see that S. What you would see is just the actual sequence, ... And you would go, well, can I even find the sum of this infinite sequence? And let me ask you, are the fractions getting smaller in value? And they appear to be, right? How do I know that? Because the numerator is growing what? But what does it look like, the numerator? Arithmetically, which are lines, and the bottom is growing what? Geometrically, which is exponential. So you can see the bottom is growing much faster than the top, isn't it? And you can see that, right? Here the top was bigger, now the bottom is much bigger. So if the bottom is growing more rapidly, then the size of your fraction is what? Just getting smaller. And if it continues to get smaller, it'll eventually become so small it's almost negligible, right? That amount will be so small. And again, like that convergent sum, like I was approaching the wall as I was having the sequence, it becomes a convergent sum. I don't know what that sum is, but that's what our task is. So this is a second kind of problem, and you will notice that it is a convergent sum. I mean, that it is this second strange sum, because you will see an arithmetic pattern in the numerator and a geometric pattern in the denominator. Now, you might go, well, we've done these before. No, we might have come up with a formula to write it in sigma notation, but we've never found the sum. Are you with me? Like, yes, I could find an arithmetic formula to represent the numerator, a geometric formula for the denominator, and that would give me a formula that would tell me what the next term was, or maybe what the 50th term was, but not the sum. So we're going to have to get really creative here to find the sum. So here's what we're going to do. When you acknowledge or notice one of these, the first thing you do is go, well, let's name it. And you're going to name it S. Or whatever, some variable. I use S because it's a sum. All right. What you're going to do with this, it's now an equation. So now that you've named it and created an equation, you're saying the sum is whatever that adds to it. We're going to try to do some clever math here and turn this thing into an infinite geometric sum. Okay. Now, right now, it is not an infinite geometric sum. It's just an infinite weird convergent sequence. So here's the process we're going to go through. The first thing we're going to do, and I'm showing a lot of work here, but when you're doing it, hopefully it won't take this much. But the first thing we're going to do is we're going to kind of ignore the numerators for a moment, and we're going to look at the denominator and say, what am I multiplying the denominator by? So 3. So since I'm multiplying the denominator by 3, and 3 is in the denominator, I'm going to use this little cheat factor. I'm going to say 1 over whatever I was multiplying by, and then I'm going to negate it. So when you look at these, ignore the numerators. Whatever I'm multiplying the bottom by, like if I'm multiplying by 4, you're going to say 1 over 4 and negate it. If I'm multiplying the bottoms by 5, 1 over 5 and negate it. And you're going to take that number, that 1 over r, so in this case, negative 1/3, you're going to take that number and you're going to multiply everything in this equation by that. And what you get, you're going to put beneath that lined up so that each matching denominator lines up under each other. Now just watch. I'm saying a lot and it sounds like it's hard, but check it out. So here's my initial value, right? My initial equation, right? If I were to take negative 1/3, what is negative 1/3 times s? Negative 1/3 s. I'm going to write that right there. Now, what is negative 1/3 times 4/3? Negative 4/9. I'm going to write it under the 9 term so that it matches up because I'm going to be adding them in a second. So I don't want to put it there because it won't add nicely with that. Here, you can see that I have the same denominator. Then I'm going to multiply that by a negative 1/3, which gives me what? That second term, negative 7 over 27. And I'm going to put that right there because it lines up. And then I'm going to multiply this one by a negative 1/3, which gives me negative 10 over 81. And I'm going to line that up right there. And I'm just going to keep doing that forever. Well, I'm only going to do it until I run out of matches, really, and then I stop. Now, watch what happens when I add these two equations together, which I can do, right? Because that's the elimination method. If I have one equation, another equation, I can just add them together. So what is 1s and a negative 1/3 s? A 2/3 s, so I write that there. What is a 4/3 plus nothing? 4/3. Now, here's where the magic happens. What's 7/9 minus 4/9? 3/9. 10/27 minus 7/27. 3/27. 13/81 minus 10 over 81. 3 over 81. Look what this forms. What is that? That is an infinite geometric. So I have essentially done some clever manipulation right here to get, and if you kind of think about it, when I proved a geometric sequence, I was kind of doing this, right? I made it to where all the terms just canceled. I can't make them all cancel, but I can make them not cancel, but now be geometric. This wasn't geometric in any way. That part is. Sometimes you get lucky and you can actually include the first term, but mostly not. So what I'm going to do now is I'm going to take out my infinite geometric sum formula and add this stuff together and just put my answer right there and add it back to the 4/3. So what is my infinite geometric sum formula for this sum right here? First term. Now that's the first term. I'm not looking at the 4/3, right? Because the 4/3 is not part of the infinite geometric sum. So the 3/9 would be the first term in the infinite part. So I take that 1/3, put it right here on the top. And then what do I put on the bottom? I did it right here. Take the 3/9, put it right there on the top, right? 3/9. And then what do I put on the bottom? 1 minus the r, which is, what is the r of that?
1/3.
1/3. So 1 minus 1/3. Of course, that now cleans up into 1/3 divided by 2/3, which if I multiply by reciprocal gives me a half. And again, don't forget this stuff. It's still here, right? I'm just cleaning up this infinite part first. But once I've got it all cleaned up, I'll have all three parts there. I can now add this together. 8 plus 3 is 11 over 6. And if 2/3 s equals 11 over 6, I can multiply by 3/2 and get 11/4. And if that's s, and s was my original problem, then my original problem is 11/4. Now, that's a lot to absorb. I find that practice makes better. Not necessarily perfect. Let's try it again. You look at it. What do you see? Arithmetic on the top. Times 2 on the bottom. Geometric on the bottom. So I go, all right, that's that second kind of strange sum. What's the first thing I do on these?
Set them equal to s.
So I'm going to call s, and that one's kind of in the way. So I'm going to say s is this. Now, then I got to find that multiplier, right? So how do I find the multiplier? If I'm multiplying the bottom by 2, what do I do? 1 over 2 and negate it. So that's what I'm multiplying everything by. Are y'all seeing this? So if I'm multiplying the bottom by 2, put 1 over 2 and negate it. So what is s? I'm going to multiply now every single thing by -1/2. What's negative a half times S? Negative 1/2 S. Bring down the equal. Now, what is 3/4 times negative a half? Negative 3/8. And where do I put it? Under the part that has an 8 for the denominator. So that went there when I multiply. And then what's 5/8 times that? Negative 5/16. So that's going to go under the 16th term. And then what's the next one times that? Negative 7/32. And I can keep going, but I'm only going to do as far as I need to be able to line these up. Then what do I do now that I have this weird new equation? Add them together. So what is 1s minus a half of an s? 1/2 of an s. And then what is 3/4 and nothing? And then what is 5/8 minus 3/8? 2/8. What is 7/16 minus 5/16? 2/16. 9/32 minus 7/32? 2/32. And what do you see here now? Infinite geometric. Now, not the whole thing, but that part, right? And again, occasionally the whole thing is, but I don't even bank on it. I just know that from the second on, it's going to be infinite geometric. And it always will be if it's this kind of problem. So all I have to do now is add this junk together, or figure out that infinite sum, add it to 3/4, and then multiply both sides by 2. So here we go. How do I figure out, I'm bringing everything over, how do I do the infinite sum? So 2/8 on the top, which if you want to just write 1/4, knock yourself out. Minus what? What is the ratio of this circle part?
1/4.
1/2, 1/2, 1/2. So 1 minus a half on the bottom. Cleaning all of that up, what does that become? That becomes a 1/4 divided by a 1/2. And to divide by a half, you multiply by a 2/1. Don't forget all the rest of this. And you end up with what? 3/4 plus 2/4. Yes, it's a half, but if I got common denominators, why not leave it like that? And I end up getting 1/2 S is 5/4. And then what is S? Multiply by 2, so 10/4 or 5/2. And if that's S, then that, which is S, must be equal to 5/2. Not too bad? Now, of course, they're going to try to disguise these from you. So look at number 2. Number 2, you see this problem and you're like, what the heck is that? And I'm going to be honest with you, if I saw that the first time, I'd go, is that geometric? So I'd probably try this. You know, if it was a normal test, I'd probably say, let me see, is 1/3/2 the same thing as 5/8 over 1? Well, 1 divided by 3/2 is 2/3. 5/8 over 1 is 5/8. Those aren't equal. So this is not geometric. And then maybe I check arithmetic. Is 1 minus 3/2 the same thing as 5/8 minus 1? And you get that, and those are also not equal. I'm like, well, crud, what else is there? And then I go, wait a minute, it might be one of these strange sums. Now, if it's a strange sum, the two you have are where the numerator is all the same. It's not that one. That's what we learned yesterday, right? Where they were all 1s or all 2s or something. Or arithmetic over geometric. And the hint to me that it might have been arithmetic was, look, 3, 5, 7. So even though that second and that fourth term right there didn't fit initially, maybe they've been simplified. So if this is supposed to be a 3, 4, 5, how could I rewrite 1? 4 over 4. So if I rewrite that as 4 over a 4, and then this is supposed to be 5, 6, 7, how can I rewrite that? 6 over a 16. Then look, it is arithmetic over geometric. So occasionally you'll see something like that too, where it will look a little nasty and maybe you have to play with it. But again, if you're going down your list, is it arithmetic? Nope. Is it geometric? Nope. Is it two geometrics woven together? Nope. Is it that first kind of strange sum? Nope. Well, then maybe it's the second kind. And that's what you would need to do, except on this test, again, I'm not going to deal with just regular arithmetic and geometrics. It would be maybe two geometrics, maybe the strange sums, or maybe what we learn in the next day or two. So what's the first step? Name it. So I'm going to call it S. What am I multiplying the denominator by? 2. So what's my multiplier that I'm going to multiply everything through by? Negative 1/2. S times the negative 1/2. 3/2 times the negative 1/2 is what? Negative 3/4. 4/4 times the negative 1/2 is negative 4/8. That times the negative 1/2, negative 5/16. It's supposed to be a 5. That times the negative 1/2. And if I keep going, which I'm not going to go any further than that. I could though. But now I've got it set up and ready to roll. So what's S minus 1/2 of an S? 1/2 S. What is the 3/2 and nothing? 3/2, and then like before, here's where the magic happens. 4/4 minus 3/4 is 1/4. 5/8 minus 4/8 is 1/8. 6/16 minus 5/16 is 1/16. And you can see the infinite geometric appear once again. So what do? I rewrite the equation. 1/2 S equals 3/2. And I can do my infinite geometric by taking my first term, which is 1/4, and dividing it by 1 minus. And what is the ratio of this? 1/2. So I end up taking 1/4 divided by 1/2, which gives me what? 1/2 at the end of the day. Because to divide by 1/2, I multiply by a 2. So if 1/2 S equals 2, then S must be 4. Right? Y'all seeing it? All right, and I could give you other ones. Like here's another one right here. I'm adding 5 on the top. I'm multiplying by 3 on the bottom. That's totally going to work that way. Check this one out. A lot of people just see that and go, I'm out. I'm assuming the position. I don't know what the heck to do on that. But again, we're better than that, right? So if I don't know what's going on there now, does anybody see that this is one of these? Why?
The top is arithmetic.
That's linear, so arithmetic.
The bottom is
That's exponential, so exponential, so geometric. So this is going to be an arithmetic over geometric. Now, if you're looking at that and going, I would not have seen that. No problem. It's an infinite one, so you got to figure something's going to happen, right? Let's write out some terms, see what happens. So on this, if I was writing out terms here, I'd plug a 1 in and I'd get -2/3. Right? I plug a 2 in and I get 0/9. And I'm going to go ahead and write that because a lot of people put 0 in there and that kind of messes them up. But I'm writing out what I see. Plug a 3 in there and I get 2/27. Plug a 4 in there and I get 4/81. Plug a 5 in there and I get 6/243. And what am I seeing here? Strange sum, an infinite geometric, right? Arithmetic on the top and a geometric on the bottom. So what do? Name it. What am I multiplying the bottom by? 3. So what is my multiplier? -1/3. So if I multiply everything here by a -1/3, I get what on the left? -1/3 S. And then on the right, what's that times a -1/3?
2/9.
Positive 2/9. What's that by a -1/3? 0.27. What's that by a -1/3? -2/81. And that by a -1/3, -4/243. And the more you do these, the more you'll get comfortable with them. You really only need 3, right? You need that first term because it more than likely isn't going to fit with the other stuff, although it might, okay? But you, when you get done with this, but you also need basically right here, these 2 terms to be able to establish what the ratio was. So what happens when you add an S to a -1/3 S? 2/3 of an S, -2/3 added to nothing. And then again, here comes the magic, 2/9. plus 2 27ths, plus 2 81sts, plus 2 over 243. And again, infinite geometric. So again, don't forget, people all the time forget this part on the left. They just find the infinite geometric and quit. You're memorizing too much. Remember, there was a system, a process that we did here. So how do I find the infinite geometric of that? First term on the top, which the first term of this is 2/9. What was the ratio of this thing? 1/3, the top by 1, the bottom by 3. So 1 minus 1/3. And I end up getting this. 2/3 S equals negative 2/3 plus, what's 1 minus 2/3 on the bottom there? 2/3. How do you divide by 2/3? You multiply by a 3/2. So I'm going to move that up there, and then I can cancel and see, oh, I'm just adding a 1/3 to that. So I get 2/3 S equals what? Negative 1/3. And if I multiply both sides by the reciprocal, what do I get? Negative 1/2. Because if I multiply both sides by a 3/2, everything cancels on the left and the 3's on the right. Y'all seeing that? So they're really not terrible. They seem terrible when you first see them, but once you see that that's just and you're like, wouldn't there be like 5 million ways to do convergent sums? Short answer, yes. There's so many different variations of these, but when you go to a math tournament, you see the same old stuff over and over. And I've seen so much. You have the gift. I'd be shocked if you saw anything at a math tournament this year, it's that you have not seen on these two, this test or this quiz, because they just seem very similar. All right, there's another one, arithmetic on the top, geometric on the bottom, right? Plus 3 is 3, times 4 times 4 times 4. So if you can do those, I think you're going to be in really good shape to do this work, but make sure you do that. That was the second part. But I want to jump into quadratic. What do I want to do? Quadratic or harmonic?
Which one's easy?
It's a harmonic.
Quadratic.
Harmonic.
Harmonic.
How much time do I have?
We get a
20 minutes.
I have 20 minutes?
No, this is a.
Okay, we're going to start quadratics. Harmonics are super easy, and that's the order that we have here anyway. So we're going to start quadratics. If we finish, great. Quadratics used to be really tough. And then over the years, because I was teaching them strictly the math, and over the years, I had these students that kept finding new and unique ways to shorten the process. So now, these really hard quadratic problems are super easy, but they tend to be a little bit more memorization. So what I'm going to do for you is show you the why of it, and then I'm going to allow you, if you know the tricks, to just use your tricks. And if we need to review a little bit of this tomorrow, great. So I'm going to go past this infinite sums. Your infinite sum stuff is for Wednesday anyway, so I'm skipping this.
We've already done some too.
Have we?
This
We
was
skipped some of the problems, but we did them.
Yeah, we did.
Yeah, remember I kind of had to change the order after I printed this because of Thanksgiving landing funny?
Wait, will we ever finish the rest of this string stuff in homework too?
Yes. I don't know if we're going to get very far with quadratics, but let's just jump here. I'm on page 79.
So it's like Thanksgiving Thursday.
That's my plan right now, unless I tell you otherwise. I mean, harmonics are a joke. I mean, super easy. Takes 5 minutes to explain
Why didn't we do harmonic?
because I got 20. Okay. All right. So here and I'd rather not teach quadratics the day before test. It doesn't give you really a chance to marinate. So here we go. Does it make sense? You know that a quadratic equation has something squared in it, right?
Yeah.
So you also know that if it looked linear, it would be arithmetic, right? But if it looks like this, that's clearly not an arithmetic. It's squared. It's not exponential because exponentials have numerical bases with powers that are variables. Well, this is just a quadratic sequence, which means, like any quadratic, your sequence could literally, as I'm writing out the terms, they could go down in value and then back up. Now, a lot of times they don't do that. Sometimes they just go up, but they're not going up exponentially if it's from this equation. They might look that way, but it's like the right side of a problem. but sometimes you'll see them drop and then climb. Okay, so anyway, if I wanted to find the first three terms, what would you do right here if I gave you a sequence and you knew A, B, and C? You plug in 1, 2, and 3 for the n, right? Because isn't n the place? So hypothetically, if you had this sequence right here, say it was Tn equals, how about just n squared minus 3n plus 4? And I said, what are the first three terms? You could plug a 1 in, and you get 1 minus 3 plus 4 is 2. Then you could plug a 2 in and get 4 minus 6 plus 4 is another 2. Then you could plug a 3 in and get 9 minus 9 plus 4 is 4. If I wanted to keep going, I could just keep going, but I would just be plugging numbers in for n, right? Plug in the places, get the terms. And again, if you see them match like that, that's probably like 2 on this part of the parabola, 2 on this part of the parabola. Now I'm heading up. Okay, so it's not uncommon to get the same number twice or to see something go down and then back up. It's not uncommon. Okay, now, what happens if you don't have the equation and I want the equation? First of all, how do you even know that it's a quadratic equation? Now, you could sit and guess and play, try to find a formula randomly. It's probably not going to happen. So let me show you something. If it is a quadratic sequence, which has an equation modeled by this, this is what always happens. When you look at these terms, look at, does anybody see it? What is the difference between 3 and 5? 2. What's the difference between 5 and 9? Between 9 and 15? 15 and 23? 23 and 33? What do you see about the differences? The differences are growing, right? Now, if I were to ask you what are the next three terms, that wouldn't be hard, would it? Because you can see that what I'm adding to 3 and then to 5 and 1 to 9 is growing arithmetically. So if I wanted the term after 3, what would I add? A 12. And then if I wanted the term after that 45, what would I add? A 14. Can you see that? So that's how you know it's quadratic. Now, if I know it's quadratic, then doesn't that mean, right here, if I know that, then doesn't that mean that the first term is 3, the second term is 5, and the third term is 9? And I can keep going, right? Well, if I know that, then technically, couldn't I say that based on my formula for quadratic sequences, that's the general formula. In fact, let's make it easy and put the Tn on the right side so it'll look prettier, and you'll see why in a second. Couldn't I say that the term is 3 when the n is what? 1. And I plug a 1 in for n, and I get an equation. Now, that's not my quadratic equation. That's just a relationship between A, B, and C. Couldn't I also say, though, that the term is 5 when the n is 2? And I plug a 2 in there, and I get 4a plus 2b plus c is 5. And then couldn't I also say that the term is 9 when the place is what? 3. So 9a plus 3b plus c is 9. And what do I have? System of equations. Can we solve systems? Lots of different ways, right? I could take the first equation and solve for a, and I could take whatever I get, shove it in there for a, shove it in there for a, and I would have 2 equations in terms of b and c, and I could solve. I could do a system like I could take these 2 together and negate the signs and get rid of c's. I could take these 2 together, negate one of the signs and get rid of c's, and I would have 2 equations with a and b. I could solve those. Heck, I could pull out Kramer's rule, right? I could find a by going that determinant, put over the a determinant over the regular determinant. And if you forgot about that, you'll get a reminder probably on your exam review. Point is, all I would have to do is solve. And that's what we used to do, solve the equation. And everybody was miserable, all right? And then along came this guy named Mark Kaplan, okay? So this is me explaining all of that right here. And you could have solved it a lot of different ways. Well, that guy named Mark Catlin, years ago, he came in and he goes, all right, Mr. Hart, I did this homework. By the way, it was very nauseating. Thank you. And he made some comment. And then he goes, but I did notice something. I said, what'd you notice, Mark? He goes, well, we always are using the first, second, and the third terms. And I'm like, well, you don't have to. I'm like, yeah, but why wouldn't you? Because plugging in 1, 2, and 3 keeps the number smaller. And I was like, that's a good point. He goes, well, if we're always using the first, second, and the third terms, then the left side of my equation always looks like this, right? I'm like, that's right. Now, the right side may not look like that because what is the right side? Those are the actual terms in the sequence, and the sequence may change, but the places don't. And the places, 1, 2, 3, are what went into that part of the equation. So he goes, well, here's what I've noticed. If the left part's always the same, I just noticed that if you multiply that middle equation, you know, the one you plugged in for the second term, if you just multiply it by -2, a little bit of magic happens. I'm like, well, let's look at the magic. So when you multiply it through by -2, I get -8a, -4b, -2c equals -10, right? He goes, look what happens when you add everything together. Not solve the system, but just kind of cheat and add it all together. Your b's and your c's go to 0 and cancel, which automatically gives you a real quickly, right? And I always get 10a minus 8a is 2a. That always happens because I'm always using the same left side. Now, the right side's different, right? The right side, you're going to have to plug the 3, 5 and multiply the -2 and then just add that stuff together. But immediately, I have a really quick way of solving for a. And we're like, Mark, that is fantastic. That really saves us a lot of trouble because now we can find a real quickly. And as soon as I find a, which in this case was 1, what can I do with it? I could plug it in there for a and there for a, and then solve for b and c with a nice, simple system. And we rejoiced. And we thought it was wonderful. Until Aubrey Wallace came along. Aubrey was not the best student and rarely did homework, but I guess this particular day she did. Great kid, though. I really liked it. She came in and she goes, Mr. Hart, I noticed something. She goes, I noticed, and this was years later, but she goes, I noticed right here, you know, we're doing this stuff and we noticed we always got 2a, right? I'm like, yeah, because if you multiply by -2, you always get 2a and the b and the c cancel. It was this part we had trouble with. She goes, well, guess what I noticed? That number, back here, she goes, that number is always, hear me out, when you write out the differences in between the terms, the common difference of those is always that number. She just noticed a pattern. So like, you know, go back to the very beginning, like right here. Do you see how this number, the difference between those is 4 and then 7 and then 10 and then 13? What's the common difference of the differences? 3. That's always what ends up being on the right side of the 2a. So now I don't even have to write the equations out. I can just go, hey, if that difference is 3, I can go 2a equals 3, a equals 3/2. And we rejoiced until, and this was the biggest rule of all. Because again, that's only giving me a, right? And if I only have a, I still would have to plug it back into at least 2 of the equations to be able to solve for b and c. And then this guy named Dmitry Gavrikov came along. We called him the Big Russian. And Dmitry and his brother moved here, and his brother was like 4 years older. I think he was in like 4th grade, and his brother was like 8th grade. His brother never shook that dark, strong Russian accent. But Dmitry sounded like a normal teenager, like one of you guys, because I guess he had had more time to pick up the language. Awesome guy, great soccer player, super smart guy, whatever. Dmitry came up and really got creative. He goes, okay, I've noticed something, Mr. Hurry. I noticed that in your formula for your quadratic, which is this, what if I found the 0 term? And I was like, well, there isn't a 0 term. He goes, well, work with me. He goes, if I plug 0 in for the place, right, then the 0 term is what? C. And I need C because I need A, B, and C, don't I? And I said, well, okay. He goes, well, watch. If I look at a term like this, and I'm going to rewrite, I did rewrite it right here. If I look at a sequence like this, right? clearly, that's my first term. That's the second, that's the third, right? So I would be looking for the 0 term. Well, if I'm adding 5, then adding 11, then adding 17, what does it look like I'm adding each more? I'm adding what? An additional 6? Well, then what would I have added to the 0 term to get to 2? -1. Do you see it? Because if that's 5, 11, the term to the left would be a -1. You seeing that? Yes? So what do I have here that when I add a -1 to it, I get a 2? If 3 is the 0 term, and the 0 term is C, I now have C. And we rejoice. Okay? Because now this is what I need, right? I need this formula, so I have a shortcut to find A, and I have a shortcut to find C. Are you with me? Well, now it's super easy because I know that the first term is T1, which was, say, in this case, 2. And I know that when n is 1, the first term, I get A plus B plus C. If I already know A, which in this case would have been 3, and now I know C, which in this case would have been 3, then all I have left is to find B. And that I can do pretty easily, right? And I'll talk you through that again. Okay, so right here, let's look at another one. If I had this right here, I could say, okay, based on this, it looks like I am, what? I'm adding 4, and then I'm adding 6, then 8, then 10. So it appears like I'm adding 2 each time. So to get to that 0 term right here, what would I have had to add to it to get to 5? 2. So what is that number? 3. So right there, I know 2 things. First of all, I know that 2A is always equal to what? The common difference. So A is 1. And then I also know that C is the 0 term. So C is 3. And then I always know that if I take this formula, which by the way, I don't do this every time, but I'm just going to say it one more time. If I plug a 1 in, the first term is just A plus B plus C. And I know the first term. It's 5. So I could say 5 equals my A plus my B plus my C. And now I have my B, my C, my A. I plug it in there and I have my formula for the quadratic. And we rejoiced. Okay? Now, the last one is not necessary. But Martina happened to notice this little shortcut last year. And I got to be honest with you, I went so long. Like, we've been doing this for 10 years. I honestly forget, like, even at this moment, I'm a little shaky on what she was doing. I forget to go back and look at it. But she noticed something, and it's a little bit off right here, but I'll show you. I mean, it's maybe a little bit shaky. But she noticed one last thing, and it might be a minor shortcut to find your B, just a minor one. But she noticed this right here. Instead of writing out T1, instead of writing out T1, which would have been 9, equals A plus B plus C, and take the A that I found and plug it there, and take the C that I find and plug it there. Instead of solving for B, she noticed something. She noticed, and we call this the Pozo principle, okay, because that sounded kind of cool. All right, that A plus B, and again, I'm already going to know A plus B happens to be equal to that number we wrote right here that separated T0 and T1. So, and it kind of makes sense if you think about it, because if I subtract the 8, I get 9, which is 1. So that 1 right there, a little last minute shortcut, you could just say, hey, A plus B equals that little number right here. And since I already know A is 3/2, I can subtract the 3/2 and get my -1/2 that way, whatever. And now I know my ABC. But I got to be honest with you, in my new keys, I'm probably using the Pozo principle, but I don't think I redid any keys for you guys this year. So in my old keys, I might not even be using that. I might be just going back up here and plugging the A in and plugging the C in and solving for B. So whatever you want to do on that. But I do want to walk you through a couple of these in the last 4 minutes. So right here, problem number 1 on the homework. Check it out. You look at it, you go through your list, you can't figure out what the heck it is, and then you go, but wait, right here, 7, 10, 13, 16. I'm increasing arithmetically, aren't I? So what does that tell me? Real quickly, that twice A is what? What that common difference would have been, which is 3. So I've got my A value. Bam. Then I go, wait, can I find the 0 term? Well, I would have to go back how much? Hold on. 4, because I got to complete that progression this way. So to go back 4, what would this have been? 8. What does 8 give me? C is now my 8. All right. Now, notice I wrote the number 4 here. So for the C value or the B value, you have 2 options. One, you could say, well, I know that the first term 12 is A plus B plus C. So that would mean that 12 equals 3 halves plus B plus 8. So if I subtract the 8, I get a 4. If I subtract that, I get a 5 halves, I think. 4 minus 1.5 is 2.5. Yes. 5 halves. You could do it that way, but you could also do what? Pozo principle says A plus B equals that box number that you wrote in there, 4. Take your A, plug it in there, subtract the 3 halves, B equals 2.5, which again is 5 halves. And then once I get my, so either way, this or this, either way, I do not care. But once you get that, what is the formula? What is it? A n squared, so 3 halves n squared. B is 5 halves, so plus 5 halves n, and then C is 8, plus 8. And I would strongly encourage you that when you're doing these, go back and double check. Like, just plug 1 in and 2 in and see if it works. If I plug a 1 in, what do I get? 3 halves and 5 halves is 8 halves, which is 4, plus 8 is 12. Okay, it's working. So all we have to do tomorrow is quadratic. Quadratic will take me maybe 15 minutes, including examples.
You mean harmonic?
Harmonic, sorry. And then we'll answer any questions you have on anything. And I think we'll be ready for this quiz. I've already printed it. It's like 10 questions, 11 questions, and a bonus.
Is it like just
Just what we've been doing this week. That's my plan, yes.
Do we need to do the quadratic problem?
You're going to have to do them eventually. So yeah, I try to knock them out if you can.
What are we gonna do tonight for homework?
Finish up the strange sums too, and then work on this. If you don't quite get finished with this, I understand. But yeah, try to knock out what you can.
So first,
So what's the quiz? The quiz?
When?
Yeah.
It says on Thursday on your assignment sheet? Yes.
Hey, Mr. How you doing?
I'm not sure if this is just like inherent, but like, you could just do these like boxes or minus competitions every two.
You guys are always class.
It said little b.
What
happened
This is the box number, which is like the.
Oh, yeah. Come back to Tuesday. So yeah, April's coding is the box.
So many gathering
That's
bro.
like-
What happened to him?
Man.
He's been corrupted. No. He went to prison.
Yeah, in my experience, when you say stop or don't, you're inviting. You're inviting.
Listen to me. My child.
Missouri, did you see my to be or not to be speech? I did the whole first.
You need to see that part anymore.
Yeah, and you probably should read mine.
I got it close. So far.
Why is Miss Reeves game?
What?
Why Miss Reeves isn't running?
Why did they
Maybe I
talk?
could get well, but
She's not here, this?
she is, but like, she, I don't know. She had her head down on her desk a little bit. Like,
Really?
she wanted to throw up.
She does get turbomyces.
I'm sure, I don't know.
No, she does. I bet that's what it is. That's.
She never misses.
Yeah, I bet that's what it is. That's not great.
Anyway.
All right, man. You give it to.
And he wants to go get help. My friend's like, Nick can help you very good.
I used it for my search.
I was like, oh, dang. Pretty sad.